G'day ladies and gents, welcome to the next lecture as part of our steel design course here at Stellenbosch University. Today we're going to be covering section classification, which is something that's relatively simple, relatively straightforward. Most people don't struggle with the calculations, but I find a lot of students struggle with understanding the concepts, why they're doing it, and then how to apply it. So we're going to talk through an example today and see how to apply this both to columns and to beams. So what I've got here is an unusual cross-section. Let's say we've taken a channel and we've welded it onto a T-section. So everything has a different thickness. Every piece of steel is a bit different, different lengths and dimensions and such. And here then is a view on it, an isometric view on it, showing it over the height. Now, if we were to load this column, either with an axial load or a moment here, what will happen is that it's going to cause compression and tension in different part of the structure at different times. And just remember, compression causes buckling, tension stabilizes. So if you've got pure compression, anywhere in the section could buckle. If you've got a moment, only that section which is in compression will buckle. So a moment like this, it would force this face into compression down here, and then eventually it would get to a stage where it could buckle. But we need to check is, can local buckling occur? And this is, you've got to make a good distinction between global buckling, which is when we load it and the entire column buckles from top to bottom, say from this support to this support, the entire column buckles out, versus local buckling, which is when you've got a thin element. For instance, here's my column, and now somewhere on the beam, it could be just about anywhere, a section experiences failure. So a section here then buckles out, like that. And this is independent of the length, whether it's 1 meters or 5 meters, it's some little section somewhere along the way then buckles out. And so if we had a look at a cross section, I've drawn it on this bottom flange, so we would have something that looks like this going there. And this would then be how it buckles. And then we can have the same thing with the web. Somewhere along the length, the web then experiences local buckling. I'm going to draw it there, for instance, where then a section of the web experiences buckling, or this other little flange could even experience local buckling. So let's just draw all of those on the cross section. So we could have the web that experiences buckling. So you'd have some sort of failure mode like this, and then goes out. Or, let me just do that again. So it could experience like that, or it could buckle out like that. Remember, these are localized effects. Somewhere along the length, it experiences that, or you could even have a section here that buckles out between the supports. And this is quite important because have a look at the difference in failure. Here, the entire flange just sort of pops out. You load it, it's a thin section, the entire flange just pops out. So then the furthest away from the support, the cross-section goes the furthest. But if we have a web, we have more support. We've got support there and support there that is preventing it from buckling as much. So now we've got almost a V or a bulge out in the section. So that is a lot stronger. So what you find in the calculations, it makes a very clear distinction between supported along one edge and supported along two edges, because supported along two edges is a lot less likely to experience local buckling. So for our section, we would need to classify all these different sections. For instance, this top flange, each side, that is supported along one edge. Whereas this horizontal section, if it was a channel on its own, that would be the length we classify. But now we've welded something into the side, so when it buckles, it's only this length and it's two edges, so it's two edges. This web, once again, is supported along two edges, and then this final flange of our T section that's been welded on is one. So we need to be very careful when classifying. It's 1, 2, 2, 1, and we treat these with slightly different equations, and those that are supported along two edges are much stiffer and much stronger. And just remember what I'm saying is that this is now local buckling, and let's start now getting into this more clearly, also the sort of phenomena of how this works. So here I've got a graph showing slenderness and then also the failure stress. Now let's say this is the failure stress of our column or beam as it gets longer. So initially I'm just going to ignore partial factors. Initially it'll buckle at Fy, the yield stress, but once again there are partial factors, phi, or depending on which code you're using, you would divide or multiply this value by something, but it would reach its yield stress, and then as it gets longer, the strength of the section decreases as buckling comes into it. Now, if we classify something and it is a class 3 section, what that means is that, for instance, this would be the stress at which it buckles. So this is a class 3 section in failure of class 3 section. So a class 3 section will never experience local buckling. No matter how long or how short the section is, global buckling occurs first. So we are always above it, class 3. But what happens is, if it's a class 4 section, we are now somewhere here. And this is the stress at which buckling may occur, local buckling may occur. And you'll see early on the failure stress of the whole column. So when you squash the column, the entire thing buckles out. Also, well, the entire thing buckles out or it hits yield. So it's those two combined gives you this curve. So you squash it, entire thing buckles out or hits yield, gives you this combined curve, because here it's basically yield, and then buckling starts coming into it. That occurs after local buckling. So we load up the column, and the stress gradually rises. And then what happens, it hits this failure stress. And this local buckle occurs before the whole thing fails. So then we experience local buckling. Conversely, now let's take a slightly longer section. Let's say we had a section that's out here. Now it's 5 meters long instead of 2 meters long. Now we start loading our 5 meter long column or beam, and the stress starts increasing. And what you have is you have normal global failure occurring first, and it never actually reaches the stress that class 4 buckling occurs at. Let's say this is 200 MPa and this is 100 MPa. No matter what happens, even though yes, it is a class 4 section, but it doesn't experience local buckling. Here, there is now our 1 meter, 2 meter long beam. This is, for instance, 200 MPa, but the total column will fail at 300 or 350. Local buckling, class 4 buckling, will occur before global. So we need to make sure, firstly, what classification are we in? It's class 3 or less, which we'll discuss soon. It doesn't experience local buckling. Class 4, it could experience local buckling. It doesn't mean it will, but it very well could. If it is a shorter section, one that is not likely to experience a lot of buckling, where failure stress is high, it probably will experience local buckling. If it is a longer section, then it probably won't experience it. But that's where you need to start running through the calcs. So what we're going to do now, let's just start running through the differences in these, and then we can see how to do it. So if this is, for instance, my compressive resistance, and this is my moment of resistance, my bending resistance, here's the different classes. We've got a class 1, 2, 3, and 4. We've got our 4 classes of sections. Now just remember, for compressive resistance, we only get class 3 and 4. We don't get class 1 and 2. You never even worry about them. So either what we do is, for class 3, we use the total area. So we just use the entire area. We don't lose any area because of local buckling. But then class 4, we have an effective area. And this is less than or equal to our gross cross-sectional area. Because remember, either it will be okay, and then we use the total area, or there's local buckling occurs, and then we have to reduce our cross-sectional area. So what will happen then is we start subtracting area from it. Let's say, for instance, this bottom flange failed. It was very thin and very long. We start removing sections from it. We would take away that, and we would make it a shorter a column effectively. So our section classification will turn our section, which is too slender, will experience local buckling, and we effectively reduce that. And so by doing that, we now have something that satisfies class 3 buckling, and then we have a reduced cross-sectional area. And the same thing works for bending, say similar approach, but here we have 1 and 2, which there you use your full plastic modulus, your ZPL, and then for class 2, your ZPL. So to experience a full plastic moment, there's full plastic stress across the whole section for class 1 and class 2. And then we get to class 3, we use our ZE. Remember, this is an elastic modulus, so as the outer fiber reaches yield, you take that as failure. These two terms are very much the same. To get a capacity, a compressive resistance, you take area times yield. To get a moment of resistance, you take a ZE times yield. And they're very much the same phenomena going on, so that's why they're both class 3. And then the same thing with class 4, we've got a Z effective, which is less than or equal to our ZE. And once again, slender sections probably use the full amount. Sections that are less slender or shorter beams, we're probably going to have local buckling first. So let's then graph that on our graph here. So let's say this is the point at which, that point there, at which local buckling occurs. So for the section on the right-hand side, we use our full area or our full Z modulus. Where on the left-hand side, then we have our effective area or our Z, which is less than that. And so we would have to reduce the cross-section. But there is another way to do this, is that this can become quite a painful process because you've got to subtract little pieces. For a section in compression, it's not so bad because you just reduce a bit of flange. One in bending, it becomes progressively worse and worse with the calculations. So another way to do this is just to think about, why don't you just drop this curve? Why don't we just change our yield stress to a lower one? For instance, let's say at 355 MPa it's class 4, so now we drop it to 283 MPa and suddenly it's class 3. So either if you find you have a 355 steel, it's class 4. Just change it to a different grade of steel, design it as a grade 283 MPa steel, and then it's a lot easier to do the calc. So either of those methods can be done. Either you reduce your area or your Z, or you just reduce your yield stress. And once you've reduced your yield stress, then you design it. And you have to back calculate this yield stress from the calculations to get it to classify. That's not too difficult though. All right, so that gives an overview of general section classification. Simple to run the calcs, but often complicated to understand what is happening. We load up a section. Does it experience local buckling? Class 4, it might. And then we just need to say if it could experience local buckling. Then we then run some extra calcs to see, is it a slender section, which global buckling occurs first, then it's fine, we use our full properties, or it's a more stressed sections, then we've got to either adjust our area or your Z, or we have to adjust the yield strength when in terms of going through the design. And that then covers everything both for compression resistant and moment resistance. Thank you.